So now we can actually start chapter 5, and we're moving on to section 5.2, which talks about proving that lines are parallel. So let's go over a little bit of vocab first. So we have an exterior angle of a triangle is formed whenever a side of the triangle is extended to form an angle that is supplementary to the adjacent interior angle. So here's your triangle. If we want to form an angle or an exterior angle, we're going to take one of the inside angles. So let's say we take this one. And then I basically just follow the side of the triangle out. I follow it out. Here's my interior angle. And the one that's right next to it is going to be my exterior angle. And what's special about them is when you put the two of them together, the interior plus the exterior angle should equal 180 degrees. The key, though, is they have to be next to each other. Now, if we're talking exterior angle, the one that's next to it is the adjacent interior. The other two angles that are not next to it are the remote interior angles. We need that going into this next theorem. Theorem 30 says the measure of an exterior angle of a triangle is greater than the measure of either remote interior angle, and it's called the exterior angle inequality theorem. So it says that the exterior angle is BCD. Therefore, according to what this theorem is telling us, this theorem is then saying that that angle, BCD, is bigger than the remote interior angles. So this is the one next to it, so this one's out, which means that this one is a remote interior and this one is a remote interior angle. So remote interior angles. So that means angle C out here, this angle right here, the exterior angle, has to be bigger than both angle B, and it has to be bigger than angle A, separately, that is. So when two lines are cut by a transversal, we went over that 8 angles are formed. You can use several pairs of angles to prove that the lines are parallel. Because even though we went over vocab yesterday, in order to be able to say that those are those types of angles, or to say that the angles are congruent, or the fact that the angles are supplementary, we need to be able to prove that those lines are parallel. So let's look at these theorems, and there's a handful of them. So we have theorem 31. It says if the alternate interior angles are congruent. So if you know in this particular case that angle 3 is congruent to angle 6, if that is true, then we can say that A is parallel to B. For theorem 32, we're talking alternate exterior. So one instance is if we know that angle 1 is congruent to angle 8, then we can say that line A is parallel to B. For 33, corresponding angles. So again, another pair of congruent angles. So if we say that angle 2 is congruent to angle 6, then we can say that A is parallel to B. Now, if two lines, this one got cut off here. So it says if two lines are cut by a transversal such that the two interior angles on the same side are supplementary, then the lines are parallel. So if this guy right here, and I can't say they're congruent because they're supplementary, so angle 3 is supplementary to 5, then A is parallel to B. You also might see it where you might know that angle 3 plus angle 5 equals 180, either one of those. All right, so we're just continuing to go through the trend of each of these different types of angle pairs. So theorem 35 says if two lines are cut by a transversal such that two exterior angles on the same side are supplementary. So these are your same side supplementary, which was not one of the vocabulary ones that we went over, but it was in that example we had done with that last diagram in the notes previously. So it says if two lines are cut by a transversal such that two exterior angles on the same side are supplementary, then the lines are parallel. So just like with same side interior being supplementary, same side exterior are also supplementary. So we see that angle 1 and angle 7, if they're supplementary to each other, then we can say that those two lines A and B are parallel. Last theorem here, theorem 36 says if two coplanar lines, so they're on the same plane, if they are perpendicular to a third line, so A is perpendicular to C, and B is perpendicular to C. If that is the case, if they are both perpendicular to that same line, then we can say that A is parallel to B. So let's practice a little bit in regards to proofs, because these topics are definitely used in proofs a lot. Anytime you see lines being crisscrossed, you should be thinking parallel lines with this stuff. So we're going to actually prove the theorem that we just talked about, Theorem 36, so we're not going to use it. But moving forward, you definitely can use that. So it says, given that AB is parallel to BD and that CD is parallel to BD, we want to prove that AB is parallel to CD. So this is Theorem 36, but we're proving it. But we are proving it, so we can't use it. So we can't use it in the proof. All right, so we have to come up with another way. So step one, we copy down our given with given. Now if we look, if we know they're perpendicular, then we know, I added the numbers here, then we know that angle 1 and angle 2 are right angles, because that's the definition of perpendicular. Well, if angle 1 and angle 2 are right angles, then we know that they're equal to each other. So they're congruent, because all right angles are congruent. Then if we know that angle 1 here, this one right here, is congruent to this one right here, whether they be right angles or not, in this case they are, those two angles are corresponding angles. So if those two angles are corresponding angles and they are congruent to each other, then we know that AB is parallel to CD. And this is the shorthand way of writing out the theorem. So I wrote corresponding angles congruent. This symbol right here means implies that you have parallel lines. But if you want to write out the whole entire theorem, please do so. You don't need to shorthand it, but maybe eventually you'll get to that point, but you want to make sure you get that comfort level down first. So number 4, again, for that line 4, let's go back up to where our theorems were. That is using Theorem 33 that says if corresponding angles are congruent, then the lines are parallel. So angle 1 and angle 2 are corresponding, so that allows the two lines to be parallel. So again, my shorthand way of writing out that theorem is that corresponding angles are congruent. That arrow means implies parallel lines. All right, let's try 2 more here. All right, so we have a parallelogram as a 4-sided figure with both pairs of opposite sides that are parallel to each other. So it says given angle 1 is congruent to angle 2, given that PQR and RSP are congruent to each other. So this angle right here is congruent to this angle right here, and we are trying to prove that it's a parallelogram. Well, all we know right now is this about a parallelogram. Eventually, we'll learn more. So I have to show that both pairs of opposite sides are parallel to each other. So based on what I have, according to this, what might be helpful is if you extend QS right here, if we extend QS more, that's like your transversal. And if we take into account, let's say these are my 2 lines right here, this one's going to get cut off. Oops. If those are my, hold on. Oop, I'm on the wrong section. Sorry. So if those are my 2 lines, I have to prove that they're parallel. Well, if angle 1 and angle 2 are congruent to each other, okay, so right here it says angle 1 is congruent to angle 2. According to this diagram, if QS is my transversal, then that means that those are alternate interior angles, and they are congruent to each other. So if those 2 angles are congruent, then the lines that they touch need to be the ones that are parallel. And that is where this line comes from right here. So PQ is parallel to RS. And again, I'm shorthanding that theorem. This was the first one we went over today in terms of the angle pairs. It said that if alternate interior angles are congruent, then the lines are parallel. So my abbreviation is alternate interior angles congruent implies parallel lines. So the parallel symbol, you may see it referred to like this. So now I got to work on the second set. So I have this larger angle right here. We were told that this bigger angle, the whole entire thing is congruent to this whole entire thing. But we already know the green angles are congruent to each other. So by subtraction, we can then say that angle 3 is congruent to angle 4 by subtraction. Then if 3 is congruent to 4, then in this case, T is still the transversal, but now you have 2 lines going in this direction, and those 2 lines touch those yellow angles. So if 3 and 4 are congruent, those are also alternate interior angles according to that transversal. So QR is parallel to PS. Same reason that 2 was. It's just a different set of alternate interior angles. And then we proved that this set of sides is now parallel to each other. So now we have 2 sets of sides that are parallel. Therefore, PQRS, by definition, is a parallelogram. So this is a nice 5-line proof. All right, final one here on the bottom. It says, trapezoid is a 4-sided figure with exactly 1 pair of parallel sides. So in order to prove that, we have to prove the 1 pair of parallel sides. Eventually, again, later on in this chapter, we'll learn more about trapezoids. So we know that 1 and 3 are supplementary to each other. And we know that 2 is congruent to 3. So 2 is congruent to 3. Now, if we know that 1 is supplementary to 3 and 2 is congruent to 3, what I'm going to use is my substitution method. So if I have 3 here and 3 here, I'm going to replace the 3 with 2 and just sub that value in. So I now know that 1 and 2 are supplementary to each other by the substitution property. So if we look at this picture, if we extended these lines, we have this line and we have this line, and then we have a transversal. Again, you're going to have to extend these guys. There's our transversal. We just said that in our proof that 1 and 2 put together are supplementary to each other. Well, if they are on the same side of the transversal T and they are in the inside, those are considered to be same side interior angles, which by definition, they should be supplementary, and they are. So if 1 is supplementary to 2, then we know that TP is parallel to RA. So we know this is parallel to this, because we can even write same side interior angles supplementary instead of this. Implies parallel lines, or if you want to write interior angles on the same side or supplementary, implies parallel lines. Whatever version of it, the theorem you want to write, but just make sure the idea is there.